if we have two semigroups S and T, and then this function f from S to T is said to be semigroup homomorphism if f of AB is equal to f of A, f of B, where this AB is the product of A and B in semigroup S, and FB is the product of two elements FB in semigroup T. So these are called as semigroup morphisms or semigroup homomorphism. So this home for any two objects means for any two semigroups, because here the objects are semigroups. The home of A comma B denotes the collection of all semigroup homomorphisms between these two semigroups A and B, and I is the same. It is the identities for any semigroup A. For any semigroup A, IA is the mapping from A to A, which is identity XIA equal to X for all X belongs to A, and clearly this is a semigroup homomorphism. This is trivially. This can be trivially. So this is a category you can easily verify, because that composition of here the composition and the composition of mapping is that is associative, and these identities of that semigroup, they act as identities. And next category is the group category of groups. And in this category, it's denoted by GRP. It's again the triplet, but here this class object, these members are called objects, members of O are called objects. Here the objects are groups. In previous example, objects are semigroups. In that example, objects are sets. Now the objects are groups here. And home for any two objects means for any two groups. Home of A comma B will be here the collection of all group homomorphisms between the groups A and B. And I is the same, it's the identity on that group A. That's also morphism here, group homomorphism. And this composition, because it is a composition, is here composition of mapping, is that's associative, and identities of that groups will act as identities. And next is the VEC category of vector spaces. Here VEC, which is VEC means the category of vector spaces. Here we have an object class O, we have a home here, we have identity I here, and here O, the objects, they are the vector spaces. So O is the collection of all vector spaces, and home is the collection of all linear transformations between the vector space. For any vector space V and W, home of VW will denote the collection of all linear transformations between the vector spaces, and I is the identity on any vector space, which is also this linear transformation. So these are the examples of categories. We can take one more example, that's top. Top means the category of topological spaces. Home I. So here O is the collection of all topological spaces. This O is the collection of all topological spaces. So here the objects are topological space, X, Y, they are all topological space. And what is home? For any two topological space, home of X comma Y will denote the collection of all continuous mappings between the topological space X and Y, because here homomorphisms are the continuous mappings in case of topological spaces, because topology is precisely the property of continuous mappings. And identity map is always a continuous map, because for any topological space X with topology tau, this identity map from X tau to X tau, it's always continuous. It's always continuous. Xi is equal to X for all X in X. And the composition of two continuous mappings is again a continuous mapping that you have done in previous semesters. The composition of two continuous mappings in topological spaces is again a continuous mapping, and identity map is always also a continuous map. So this is a topology. This is a category, and this is called the category of topological spaces. But in these examples, we have seen that this object set is the collection of sets, home set is the collection of mappings actually, and I is the identity mappings. In general, they are not sets, but we are not interested in that. So we are interested in the category of semigroups actually, and here the objects are the semigroups, and home of A comma B between two semigroups A and B, it's a collection of all semigroups morphisms between the semigroups A and B. So this was the concept of category. So now we defined epimorphism, and we define epimorphism in category, and we will see that these epimorphism, we'll see this epimorphism and surjectimorphism. We see that these two concepts, the relation between these two, and we will see that every surjective morphism is epimorphism, but epimorphism is not true in general. It's not surjective morphism in general. But in case of groups, they are one and the same. Epimorphism and surjective morphism, it's one and the same. But in case of semigroups, they are different. Epimorphism does not imply surjective morphism. We will give an example. So that's why this semigroup is very important in category. As a category, it's very important. It's more important than the category of groups, because in case of groups, we don't have to see anything, because they are actually equivalent. But in case of semigroups, they are not equivalent. And a lot of research have been done in this semigroups, where we have characterized certain class of semigroups where epimorphisms are always surjective morphisms. But in general, it's not true. We will give some examples. So let me first define epimorphism. So suppose we have a category of semigroups. Let's see be the category of semigroups. Let's see. So let me define epimorphism. So let's write here epimorphism first. Epimorphism. Let C be the category of semigroups. Category of semigroups. A semigroup morphism, or we can say a morphism here, a C morphism here, which is a morphism between the semigroups. A morphism alpha from S to T. So whenever we write here morphism, it means it is a semigroup morphism, and S is a semigroup, T is also a semigroup, because we are in the category of semigroups. A morphism alpha from S to T is said to be an epimorphism. We write this as epi for short. If for any two morphisms, again they are semigroup morphisms, beta gamma from T to some other semigroup T to W, such that this alpha beta is equal to alpha beta gamma. The composition is same. If this composition same implies that beta is equal to gamma, then we say alpha is an epimorphism. So that is alpha is left cancellative. It's left cancellative because it is on the left hand side, and we can cancel this alpha. So any left cancellative, we call epimorphism is actually left cancellative. So that is the definition of epimorphism in category. Categorical definition of epimorphism. Here the category is the category of all semigroups. Now we will show that every surjective morphism, if alpha is a surjective morphism from the semigroup S to semigroup T, we will show that this alpha is also epimorphism. And we will also see that the converse is not true. If alpha is epimorphism, then it may not be surjective morphism in general. So let's first prove that every epimorphism is surjective morphism. Every surjective morphism is epimorphism. Every surjective is, example, every surjective is epimorphism. again we take the category of semigroups here. Let alpha from S to T be any surjective map between the semigroups S and T. Suppose it's any surjective map between the semigroups. In fact, it may be morphism here. It's a surjective map between the semigroups S and T. Now we show that alpha is subject to morphism. Right. We show that alpha is epimorphism. We show that alpha is epimorphism. So to prove alpha is epimorphism, we have to take any two morphisms, beta gamma from T to W, such that the composition is same as alpha beta is equal to alpha gamma. We need to show that alpha beta is equal to gamma. So let's take any two morphisms. Then beta and gamma from T to W be two morphisms, be any two morphisms between the semigroups T and W, such that alpha beta is equal to alpha gamma. We show that beta is equal to gamma. In order to prove this, alpha is EP. So we show that beta is equal to gamma. So in order to prove this beta is equal to gamma, we need to show that they are equal on at every element of T. So that T beta is equal to T gamma for all T belongs to T. That's what we have to prove. So let's write this as star. This is given. Star. Now let T be any element of T. Let T be any element of T. Now what's given here? Alpha is surjective map from S to T. Since alpha from S to T is surjective, so therefore there exists S in S such that S alpha is equal to T. Image of S under alpha is equal to T. Now we show that T beta is equal to T gamma. Now T beta, it's equal. What's T? T is S alpha. So it's S alpha beta. That's equal to S of alpha beta. But we know we are given that alpha beta is same as alpha gamma. So it's S alpha gamma. That's equal to S alpha gamma, which is equal to T gamma. So therefore T beta is equal to T gamma, which implies beta is equal to gamma, and hence alpha is P. And hence alpha is epimorphism. So this proves that in the category of semigroups, every surjective morphism is epimorphism. Now we show that this converse is not true in general. Converse is not true in general. Converse is not true. Every epimorphism need not be surjective morphism. Every epimorphism need not be surjective. APs are not surjective in the category of semigroups. So let's take this semigroup. Let U equal to this set, closed interval 0 to 1, and S equal to this set, closed on 0 and open on this 0 to infinity. Then you can easily verify that U and S, they are semigroups with respect to multiplication. Then U and S are semigroups with respect to multiplication. Now let's define, let I be the inclusion map. Let I from U to S be inclusion, that's any xi, image of x is equal to x for all x belongs to U. It's inclusion. It's the inclusion map. Then clearly this is not surjective, because suppose we have two elements here S, but 2 has no preimage, because we don't have 2 here in this semigroup U. So that means this map is not surjective. Then I is not surjective. Then I is not surjective. Then I is not surjective. Clearly it's morphism. It's not surjective morphism. It is morphism but not surjective. Okay. And this I is semigroup. Morphism. It's semigroup morphism. So we show that I is epimorphism. Morphism. It is morphism. Now we show it's actually epimorphism. We show that I is epimorphism. I is epimorphism. So for this, let's take any semigroup. Let this beta comma be any two morphisms from S to T, where T is any other semigroup. Be semigroup morphisms, be semigroup morphisms be semigroup morphisms so such that I beta is equal to I gamma. That's I beta equal to I gamma means if I take any element x, because I beta is a map from because as I is a map from U to S, beta is a map from S to T. So I beta is a map from U to T, and I gamma is also mapped from U to T. That is this x of I beta is equal to x of I gamma for all x belongs to U. That's equal to closed interval 0 1. So that means that is because Ix is same as x, I is its inclusion map. X beta is equal to x gamma for all x, with the x is in this interval 0 to 1. So it means 0 less or equal to x, less or equal to 1. But we need to show that, since we had to show that I is epi. So epi means that means this it should be cancellative. In other words, it means that beta should be equal to gamma. So in other words, it means that x beta should be equal to x gamma for all x in S. But here they are equal for this range of x. But we need to show that they must be equal for all x belongs to 0 to infinity. So in between 0 and 1 they are equal, but now we take the case if x is greater than 1, then x beta should be equal to x gamma. So to prove So to prove x beta is equal to x comma, to prove x beta is equal to x comma for all x belongs to S, which is equal to 0 to infinity, it is sufficient to show that x beta is equal to x comma for all x greater than 1. Because for x lying between 0 and 0 less or equal to x less or equal to 1, they are already equal. So now it is sufficient to prove this equation for those values of x greater than 1. So let's take x greater than 1. Let x greater than 1. Let x be greater than 1. X be greater than 1. So then we see that then x of g, then x of beta, x beta is equal to 1 into x of beta, because 1 into x is equal to x. Since beta is the morphism, it's 1 beta into x beta. And that's same as what's x? X can be written as x into 1 by x. And 1 of beta is same as 1 of gamma. Actually, it's 1 gamma. Because image of 1 under beta is same as image of 1 under gamma, as beta is equal to gamma for x 0 less or equal to x less or equal to 1 into x beta. So this is equal to, we can write this 1 as x into 1 over x. X into 1 over x. As x is greater than 1, there is no problem in writing 1 over x. X is not equal to 0. It's into x beta. Now again, apply the morphism property, because gamma is morphism. It's x gamma into 1 by x gamma into x beta. And here, since x is greater than 1, 1 by x is less than 1, and for any value which is less than 1 and greater or equal to 0, beta and gamma, they are same. So it's equal to x gamma 1 by x beta into x beta, because 1 by x is less than 1 and it's also greater than 0. And in this range, beta and gamma, they are same. So this is equal to, this is here what, it's x beta. Here, yes, it's x beta. X beta is gamma. Now apply the morphism property of beta. It's 1 over x into beta. That's equal to x gamma into 1 beta. But 1 of beta is 1. It's equal to x gamma. So thus x beta is equal to x gamma. So therefore, x beta is equal to x gamma for all x belongs to S, which is equal to 0 to infinity, which implies beta is equal to gamma. So thus I is epimorphism. Thus this I is epimorphism. So this proves that every epimorphism need not be surjective, because I is not surjective but epimorphism. And in case of groups, in the category of groups, epimorphism and surjective morphism, they are same. So that's why this we study these semigroups, because we want to characterize those semigroups for which epimorphisms are always surjective morphisms. So now in the next lecture we give some basic notions of semigroups, and we give the definition of semigroups, then we give certain properties of semigroups. Thank you.